Okay, so thank you everyone for coming. I know in this unusual format. It's my great pleasure to introduce for you Burke Uston. Burke is currently a postdoc at Harvard, working with David Parks, Flavio Lupin-Calmon, and others. He's doing really excellent work sort of at the intersection of machine learning and the human-centric aspects of the usability of those systems, right? Everywhere from fairness to interpretability. Much of his PhD was also in this space, which he completed at MIT with Cynthia Rudin. And I don't want to cut too much into his time, so without further ado, I give you Burke.
Great, yeah. Thank you, Jamie, for that introduction. And yeah, thank you everyone for being here today. I realize that this is a weird time in human history, and I just appreciate that everyone has made time to be joining us live. So yeah, let's get started. So I wanted to start with a milestone in machine learning. So this is an event that you won't find in a lot of textbooks, but it did make the front page of the New York Times back in 1961. And what happened was a small financing company came up with a new way to make credit decisions. So to understand what was so groundbreaking about this, you need to know just a little bit about what credit looked like before 1961. So back in the 30s, we already had systems in place to make credit decisions. If you need a loan at a store, you would find a credit manager. They would call a credit bureau, and then they'd use your credit report to decide whether or not to lend you money. And most credit managers had systems in place that could help them structure a decision, but they were just built using rules of thumb. And we had just started to develop statistical methods to learn these types of systems from data. Linear discriminant analysis, for example, was introduced around this time, but it required so much computation that people thought we would basically have sentient robots before we could actually apply LDA. So what changed in 1961 was that computers came along. And for the first time, we took our credit reports and we converted them into machine-readable format. We then used them to fit an LDA model. And then we deployed that model to make lending decisions. And then finally, we showed this entire system produced tangible benefits. In this case, it was fewer bad loans, better credit access. Now, since 1961, we've taken these first three steps and we've called it machine learning. And we made it possible to apply machine learning in just a few lines of code. And it's now easier than it's ever been to fit models in entirely new domains. And in a domain like healthcare, for example, these models could help us screen for critical conditions, simplify hospital operations, and generally improve health outcomes. And for the last few years, we've been doing this, right? We've been building hundreds and thousands of models, but we aren't hearing nearly as many success stories. So what's happening is that we're applying machine learning to settings where there is no prior use case. And we're running into problems outside of our traditional pipeline. And these are what I call last mile problems. So sticking to healthcare, I see two big categories of last mile problems. First is disuse. Here we're building models, but we're not reaping their benefits, and that's because the models aren't being used. And the themes behind disuse are issues of trust. We're basically building black box models that doctors can't scrutinize and don't feel comfortable using. And another big theme is customization. We're building generic models that don't take into account the costs or the constraints of our end users. Now, an entirely different category of last mile problem is misuse. So here we're building models, they're being used, but we're not reaping benefits because they're inflicting harm. And those harms usually relate to issues like fairness, like privacy, like autonomy. And a big theme here is that the harm is usually invisible. So in a lot of these cases that we hear about, we didn't know that machine learning models could inflict harm. And I guess what's regrettable is, had we known, we might have been able to fix it. So a big technical challenge here, I think, is knowing how machine learning can inflict harm before we actually deploy it. So my research develops methods to deal with these two last mile problems. To deal with disuse, I focus on creating models that are easier to understand and customize. And then to address misuse, I focus on understanding how machine learning can inflict harm, and I develop methods to prevent that harm. My expertise is in optimization, and I generally use that to create reliable methods, typically by solving hardware optimization problems. Now, I think that a big part of the reason why we're seeing last mile problems today is because, for the last 60 or so years, there's been this natural disconnect between people who are developing methods and people who are applying them. So as part of my research agenda, I work a lot on real world applications, and I use that to figure out, what it is that makes methods useful in practice. And every now and then, this work leads to models that are deployed in the real world and that produce tangible benefits. So what I want to do today is present methods that are designed to deal with each type of last mile problem. And each project that I'm going to talk about will involve different types of hard optimization problems, and will focus on different types of machine learning applications. So for this use, I'm going to talk about a method to build simple models that are readily adopted in medical decision support. And then for misuse, I'm going to talk about how machine learning models can violate autonomy in consumer-facing applications, and how it can design tools to protect against this type of harm. So this first project is about these simple models called risk scores. So what I thought I'd do is start with an example. So here's the CHA2DS score. This is the de facto model that's used to evaluate stroke risk. This is a model that is on medical board exams in the United States, and it's used by thousands of primary care doctors and cardiologists every single day. So this is just a simple linear model to predict stroke risk. It's got 5 factors. Each factor has a certain number of points. The way this works is a doctor seeing a patient. They'll go through the factors, add up the points to get a score, and they'll use the score to look up an estimate of stroke risk. And then that risk estimate is used to inform treatment decisions, like whether to put a patient on a blood thinner or an aspirin. Now, CHA2DS is just one scoring system, but there are hundreds of others like it in medicine. And all of them have the same format. They're just linear models with small integer coefficients. And if you ask doctors, they'll give you all sorts of reasons why they love these models. They'll say they can memorize it, they can make predictions by hand. But honestly, for the last few years, we've had apps and websites in place that have scoring systems on them. So doctors don't have to memorize or add anything. And they're still just as passionate about creating these models with small integer coefficients. And the reason why is because, well, they can really understand how these models work, right? So in comparison to a neural network, I can take a scoring system and I can print it out on a sheet of paper, and I can show it to a doctor, and they'll see all of the variables and understand how the model is combining them to make its prediction. And what the integers let them do is understand how the model works by making quick predictions. So let me just flesh this out a little bit and tell you why it's different from standard linear model. Say, for example, I want to know when CHA2DS predicts a stroke risk that's greater than 4%. And that's an important threshold to know because that's when I might be prescribing a blood thinner. So from table, I know this happens whenever the CHA2DS score exceeds 2. Here's that decision rule. All I've done is replace the input variables with x's. Now, when I show something like this to a doctor, the math is easy, and they can quickly check the values of x that satisfy this condition. And they might even figure out that this condition holds whenever x5 is true, or whenever at least 2 of the other x's are true. And so in that way, they know the model will assign a risk of 4% to patients who've had prior strokes, or who show at least 2 of the other risk factors in CHA2DS. And now that is a complete understanding of how the model operates at this decision point. And that leads to a complete understanding of when it would lead to a prescription of blood thinner. Now, here's another version of the decision rule. This is the same condition, holds for all the same values of x. All I've done is replace the integers with real valued coefficients. Now, when I show something like this to a doctor, they no longer do the math. But in fact, we've trained them to interact with this model differently. Here, the best doctors are in regression mode. They're going to check the individual coefficients. They're going to ask if they're significant. They're not even going to look for this complete understanding, even though it's there. So to sum things up, the integer coefficients are important because they let people check how the model operates and because they lead them to interact with the model in the right way. Now, the thing about scoring systems is that it's hard to build them. On one hand, you've got to build a score that will perform well, but you're constrained to fit models from a really simple model class with few terms and small integer coefficients. And we're going to see that, simple strategies like rounding are going to affect performance in unexpected ways when we're working with this type of model class. But there's this whole other issue with these types of models, which is that people actually interact with them, right? So if they're going to use them, they're going to want them to be usable. If they can understand them, they're going to want them to be aligned with domain expertise. So if you want to get your model adopted, you're going to have to address additional constraints. And these are constraints that are going to relate to what the model looks like, the types of variables that it uses, or how it makes predictions. And they're constraints that you can address, but that are going to change from one problem to the next. So in practice, if you look this up, you'll find that every scoring system is actually built differently. And there are two big approaches. So sometimes what people do is that they combine methods with different heuristics into giant pipelines. So here's a pipeline that was used to build a risk score called TIMI. And I'm just showing you this to make the point that it isn't just logistic regression plus rounding. There's several layers of feature selection, there's binarization. And the issue with something like this is reliability, right? So this worked for TIMI, but it might not work on a new data set. And if it does, then you can't tell if it's going to give you the best possible model for that data set. And that's something that's concerning because models like TIMI are used to support important decisions. Now, the other thing about this approach is that it requires a statistician on staff. It could take weeks to fix when it doesn't work. So sometimes people will just skip all of this and build the model by hand. So this is what happened with CHADS2. In this case, they had the data, but they designed a score using a panel of experts, and they used the data they had to validate the model. So during my PhD, I developed two methods to learn scoring systems from data. So that we wouldn't have to do them, using panels of experts or giant pipelines. So the first method was for these models that output yes/no decisions. And second was for models that output risk estimates. And both methods fit models by solving hard optimization problems. And at high level, this was to produce scoring systems that performed well, that could easily be customized, and that would produce useful guarantees in model development. So I'm going to focus on the second set of methods today. So over the next few slides, I'll talk a little bit about the method, and then I'm going to talk about how we applied it to build risk scores for adult ADHD screening and ICU seizure prediction. Okay. So let's just jump right in. I'm basically going to treat this problem of learning risk scores from data like a standard classification task. I'll assume I'm given a data set with endpoints. These are features and labels. And then I'm going to represent scores as a linear model. Here, the lambdas are the coefficients. So each lambda is the number of points for a specific feature. And if a lambda is 0, that means the feature is not included in the model. And then to go from scores to risk estimates, I'm going to work with a risk model. So I'll work with the logistic model, but generally speaking, everything I'll present will work for any risk model that has a convex log likelihood. And then I'm going to evaluate the quality of my risk score using two metrics. The first is going to be risk calibration. That's going to look at whether the predicted risk for my model is equal to the observed risk I observe in practice. So that's something we can check using a reliability diagram and that we can track using calibration error. So that's cal. And then the second metric I'm going to look at is rank accuracy. So this is going to look at the ability of my score to order examples in terms of observed risk. So that's something that we can check using an ROC curve and that we can track using AUC. So generally speaking, risk calibration is my primary objective, but I'm going to report ranking just as a way to track the accuracy of the model, make sure it isn't trivial. So to learn risk scores, I'm going to solve an optimization problem. What this thing will do is that it's going to take in data and it's going to spit out the vector of coefficients. And those are going to be the coefficients of a risk score called risk slim. So here, the objective of my optimization problem is minimizing the logistic loss, or it's maximizing the likelihood under the logistic model. And then my constraints are imposing the basic requirements of a risk score. So a few terms, small integer coefficients. So this looks a lot like standard empirical risk minimization, and it is. The difference here is that this is hard to solve, right? So here you've got this nice convex loss function, but you've also got discrete constraints. And as a result, this is a mixed integer nonlinear program. This non-convex, it's NP hard. So when you're faced with something like this, there are usually different approaches that we can take. Sometimes what you might want to do is relax constraints, make it computationally tractable. But we're going to be interested in solving this problem directly. And over the next few minutes, I'm going to describe some of the benefits of this approach. But just sticking to the slide, the first benefit is customization. So, in some sense, when we're willing to solve this directly, what we're saying is that we're willing to work with discrete variables. And we can use those variables to address all sorts of problem-specific constraints, right? So for instance, instead of setting a threshold on a variable like age, you can add variables that use all possible thresholds, and then you can add a discrete constraint to pick one. And then by solving that optimization problem, you would have optimized over your choice of threshold for age. So more generally, you can use this type of strategy to handle any type of constraint on the model form or its predictions. And that could be as simple as a monotonicity constraint or as complex as a group variance constraint. And in each case, the advantage is that you're going to be able to deal with these constraints directly and without parameter tuning. So what this is going to do is that it'll simplify model development. Remember before I was building risk scores using pipelines and panels of experts. Now I have a simple step process. Doctor comes to me with their data and their model requirements. I'm going to formulate a customized instance of this risk score problem, and then I'm going to solve it to obtain optimal risk score. And then the model I'm going to get is going to come with guarantees, right? So the model is going to be guaranteed to obey all the requirements that the doctor specified, and it's also going to be guaranteed to optimize loss. And in our setting, this optimality guarantee is actually meaningful. So to show you this, here's some experiments on the mushrooms data set. So this is just a standard benchmark data set in machine learning. And what I've done here is that I've fit risk-slim models for model sizes between 3 to 10. And on top, I'm showing you their loss on training data. And on the bottom, I'm showing you their calibration and their AUC on test data. So going from top to bottom, this plot at the top is basically what I'm guaranteed, right? So by definition, risk-slim is guaranteed to fit a risk score that will attain the smallest logistic loss at each possible model size. And what I'm trying to show in the slide is that this translates into good calibration and good AUC. And there are good theoretical reasons for this, right? So minimizing logistic loss maximizes the lower bound on AUC. And then minimizing logistic loss also maximizes calibration under the assumption that the logistic model is a good risk model. And it turns out that's a decent assumption to make because we're doing feature selection. So we basically have a lot of degrees of freedom in choosing features that satisfy this assumption. So these are relationships that hold on the training data. And in this case, what's going on is that they're generalizing the test data. And that's because we're fitting sparse linear models. The hypothesis set is small. And so there's generalization. And we'll see this type of generalization later on in the applications as well. So big picture, these are relationships that are going to help us in model development, right? Say, for example, I fit a scoring system with 3 terms, and I'm not happy with the way it performs. Well, now I know that I can obtain better loss by relaxing these constraints, maybe fit a model with 5 terms. And I also know that I can expect this gain in loss to translate into a gain in calibration and an AUC. Now, I showed you how this works for a simple model size constraint, but this type of relationship will hold for any other type of constraint. And what it will do is that it will help us inform model development. So everything that I presented until now really depends on our ability to solve this optimization problem. And in fact, solving this was really the hardest part of this project. So over the next few slides, I'm going to talk a little bit about how we did it. But just sticking to the slide, the first thing you should know is that the first thing we tried was to solve this problem directly using a commercial mixed integer nonlinear programming solver. Okay? So we tried several of these things, and they all did pretty badly. And on the surface, there were different reasons for this, mainly because they were using different implementations with different algorithms. But at its core, what was happening was that each algorithm was struggling with data-related computation. Okay? So just to dive a little deeper into this, basically, in our setting, the objective of our optimization problem is this loss function. And so what that means is that, when we want to compute the objective or gradient, we first have to compute that function for every single data point, and then we need to take the mean. And this type of computation will add up if an algorithm has to do it at every single iteration. So because of this, I started looking into cutting plane algorithms. And now these are just inner approximation algorithms that have been around since at least the 60s in the optimization literature. But they were really successful at solving large-scale machine learning problems back in the 2000s. And at a high level, the key to their success was instead of optimizing a loss directly, they would optimize a surrogate loss function that was much cheaper to evaluate. So we designed a new cutting plane algorithm for this problem. But before I can show it to you, I first need to tell you a little bit about how cutting plane algorithms work and why the traditional ones fail in our setting. So the first thing you should know is that cutting plane algorithms are called cutting plane algorithms because they build a surrogate loss function using cuts. And cuts are just supporting hyperplanes to the loss function that are placed at different points. And the main difference between algorithms is in terms of where they place the cuts and how they place these cuts. So in a traditional cutting plane algorithm, something like Kelly's cutting plane algorithm, you would place the cuts by repeatedly minimizing the current surrogate loss. So to show you how this works, say that you want to minimize this smooth convex function. Okay? So in a traditional algorithm, you'd start off with a point. You would then compute the objective and gradient of your function at that point. That would create this cut. And then you know that your loss got to be positive. So your first surrogate loss function is actually this blue L shape right here. Okay, so at the first iteration of your algorithm, you'd minimize your surrogate loss. That would give you this point. You would then add a cut and update your surrogate. And then in your next iteration, you'd optimize your surrogate again. Get the best point, add a cut, update. And then again. And now eventually, the minimizer of your surrogate is going to be equal to your actual function value. And that's when you know you solved your optimization problem. So this doesn't work in our setting, and that's because we're optimizing over integers and other discrete constraints. So in this case, the optimization problem we have to solve at each iteration is a mixed integer program. So that's called a MIP, MIP. And what happens is that basically at each iteration, you have to solve a MIP to add a cut. And the MIPs you have to solve get harder and harder to solve because they contain these surrogate loss functions with more cuts. So after about 200 cuts, no matter how big your data set is, it just takes too long to solve this MIP to optimality. So your algorithm stalls, and you run out of time, and your algorithm stalls. So let me just show you an example of where this happens. Here, for example, we ran this algorithm on a 20-dimensional problem, and we were able to run it for about 70 iterations. At this point, we had a MIP with 70 cuts, and it took over 10,000 seconds to solve. So we ran out of time, the algorithm stalled. And then here, I've tracked the optimality gap of the best solution over time. This is a graph that's supposed to go down to 0. In this case, it stays up at 100%, doesn't go down at all. Okay? And this isn't even a very large problem. So we designed a cutting plane algorithm that doesn't stall. And the way it does this is by building a surrogate loss dynamically through a single branch and bound procedure. So at a high level, what's happening is that we will be optimizing a coarse surrogate loss function over a discrete region using branch and bound. And so, each time our branch and bound tree finds an integer feasible solution, we add a cut. And then in this way, we're building a surrogate loss function as we go. And our algorithm is bound to eventually recover the optimal solution because our branch and bound tree will either explore all the feasible solutions and it'll only discard regions that are provably suboptimal. So this overcomes stalling. And the reason why is because, well, I'm no longer solving a MIP to add each cut, right? Another way to think about this is, my algorithm is building a single branch and bound tree, whereas the previous algorithm was building a branch and bound tree to add each cut, right? So here, for example, you can see that the algorithm is progressing, adding cuts every 1 to 10 seconds, and the optimality gap eventually goes down to 0 as it should. Now, the benefit of all of this is that we can now work with a surrogate loss function in our setting, right? And what that means is that we can fit the best model in a way that has a limited number of interactions with data, right? So in a cutting plane algorithm, the only time we ever interact with data is when we have to add a cut. And in that case, all we have to do is compute the value of the loss and the gradient of the loss once. So those are operations that scale in the number of samples. So what you get with this type of algorithm is scalability. Okay. So here to show you this, I've used our algorithm to fit risk scores on a simulated data set where I can arbitrarily increase the number of samples. And I plotted time that the algorithm spends on different tasks. And what I see is that, as I increase the number of samples, the time that's spent on model search is roughly constant. And the increase in runtime comes from computation. Now that is computation that increases linearly in sample size, because here both these axes are logarithmic. So this is a relationship that holds for all cutting plane algorithms, but in our case, we can do it for hundreds of dimensions instead of just 15. And the way that we see it is, at this point, we've overcome this fatal flaw in algorithm design for our setting. So it's now worth improving this. And so we do that. We'll reduce the time for cut computation by exploiting properties of model class and by focusing on low-level computational operations. And then we'll reduce the time for model search by designing heuristics and by deriving bounds that help us reduce the search space. And as a result, we get certifiably optimal risk scores for most of the data sets we'll work with, and that's within minutes. And when we don't, we will get models that perform well, along with a small optimality gap that helps us in model development. So that's all I wanted to say about algorithms. And what I want to do now is, shift gears and start talking about a couple of applications. So this first application I'm going to talk about is adult ADHD screening. So this was a collaboration with psychiatrists at the Harvard School of Public Health. And yeah, just a little bit of background about this. So this is an application where we had data from a national mental health study. And in this study, patients basically had to answer a set of 29 questions that were related to adult ADHD symptoms. And so they were given this questionnaire, and they filled out the questionnaire. And after filling out the questionnaire, they were given a full adult ADHD diagnosis through a diagnostic interview with 3 psychiatrists. So here we had the answers to their questions, and we had this gold standard diagnostic that was given to us by 3 psychiatrists. And we had to use this data to build a risk score that would use the answers to some of their questions to predict their risk of ADHD. And basically, if their predicted risk of ADHD was high, then a patient would know to go and get a proper diagnostic for ADHD. So this is just a simple screening example. So this is an application that I was excited about because there was basically a previous model that we wanted to update. And the model that we had to build had to look like this. So out of 29 questions, we had to choose a certain subset. Then we had to assign an integer number of points to each response. And then those points had to increase as the responses became more frequent. And that's because each question was related to an adult ADHD symptom, so you'd expect that type of monotonicity. So this is one of those models that was created with a pipeline and took about 6 months to create. And that's because one of my collaborators who also worked on this model was absolutely determined to find the best possible model for this data set. So they tried lots of different techniques to choose the questions, to assign points, and so on. And they originally wanted a risk score for this application. They eventually gave up, and they settled on a decision-making model that would just output yes/no predictions at a certain level of sensitivity and specificity. So here's a model that we produced. Okay. And I'll leave this up here for a bit. And if you want, you can answer these questions, add up the points, and then check your risk of adult ADHD. So in our case, it was really easy to take these model requirements and encode them as constraints into the risk score problem. And then using our algorithm, we were able to fit optimal risk scores in just a few hours. And then this simplified model development to the point that we actually fit over hundreds of models for this thing. So we varied the number of questions, the types of questions that were assigned, and the points that we assigned. And each time we were able to get a model that was certifiably optimal and that we were confident represented the best possible performance for that specific set of constraints. So by comparing any 2 models, we had a good idea of what we were trading off in terms of performance by going from one set of requirements to another. And because of this, we were able to customize this model in an informed way. So each time we would just take the model like this, and then we would print it out along with its performance on a sheet. And the performance was summarized through these two plots. So here, I'm basically showing you the reliability diagram for that risk score on the left and the ROC curve on the right. And in the black, I'm showing you the performance of the model on training data. And in the gray, this is the performance of the model on test data on cross-validation folds. And so here you can see, for instance, that the model does remarkably well and that its performance generalizes. But this is a healthcare application. So cross-validation is important to make sure the model isn't overfitting, but it doesn't really mean as much as validation on a completely independent data set. So here we test the model using data that was collected at an adult ADHD clinic at NYU. So here's the model's performance on that data set. Now this is a completely different population. So there's a slight decrease in performance because of data set shift, but you can see that this model still does remarkably well. And then compared to the DSM-4 model, our model performs much better, but it's also way more functional, right? So it provides several operating points that perform better. And for each operating point, it provides a risk estimate that helps us choose the operating point we want to deploy the screener at. Okay, so this next application I want to talk about is ICU seizure prediction. So this was a collaboration with neurologists at Massachusetts General Hospital and the University of Wisconsin. And then just a little bit of background about this application. So basically, patients who have severe head injuries are brought into ICUs, usually in a coma. And in this state, they can sometimes have seizures that lead to long-term brain damage. So this is damage that we can prevent if the seizures are caught in time. But the issue is that the patients are in a coma, and so the only way you can really see these seizures is with a device that's called a CEG. So a CEG is a device that measures electrical activity in the brain using electrodes, and it plots them out on a display or a printout. And neurologists are trained to recognize different patterns as CEG output, and they know that some of these patterns are associated with seizures. So in this application, we had a data set of annotated CEG recordings, and our collaborators wanted us to build a risk score that would let a doctor check for certain patterns in CEG output, and then use that to predict the risk of seizure for that patient over the next 24 hours. And in this case, the risk estimate would inform whether or not to keep the patient hooked on to a CEG device. So the other thing you should know is that CEGs are expensive machines. There's only a few of them available at any given ICU. So if a patient is at low risk for a seizure, you take them off the CEG so that you can use that device on someone else. So in this case, our collaborators wanted a simple model that was easy to use and easy to understand. Their model requirements were a little less stringent. So I can show you some of the problems that occur when you try to build a risk score using existing approaches. So here's a model that's very similar to the one our collaborators came to us with. This model that's built using logistic regression with an elastic net penalty. And here I'm showing you its score function at the top, its reliability diagram on the left, and its ROC curve on the right. And this is a model that basically performs pretty well if you just look at summary statistics like AUC and calibration. So here the issue are these risk estimates. So ideally these should be spread out evenly across the 45-degree line. And in this case, they're not. There's this kink. And that's occurring because of monotonicity constraints and score function, as well as this additional regularization that's coming from the elastic net penalty. And in practice, what this says is that the risk estimates are unreliable, right? Basically here as the predicted risk increases, the observed risk increases, then decreases, then increases again, right? So you can't use something like this to allocate CEGs at an ICU. So in practice, something like this would preclude deployment. But say for a second that we ignore this and we want to go ahead and deploy a risk score, maybe a model that would let us make predictions on the bedside. So one strategy would be to take the score function and to round it. But in this case, you can see that a lot of these coefficients in the score function are small. So if we rounded, we would eliminate all these features. Our AUC would drop. Our risk estimates would look like the stump. And then maybe another simple strategy would be to scale the coefficients before we round them. In this case, we would preserve all that information, and we would have fixed our AUC. But now our risk estimates look even funnier than before, right? And that's because our risk model isn't scale invariant. So at this stage, you might want to do some kind of post hoc calibration, maybe something like Platt scaling. So what that would do is that it would take the risk estimates, it would center them onto the 45-degree line, and it would stretch them. But it wouldn't get rid of this kink. So here's the model that we get when we optimize directly. And here you can see the risk estimates are nice and spread out the way they should be. So this model has good calibration, good AUC. Again, it generalizes. So this is certifiably optimal. It was trained in a few minutes. And when we showed this to our collaborators, they were generally just thrilled with this, just because it obeyed all their different requirements and it performed well. So they called the model 2 helps to be, based off of different features that it uses. And then earlier this year, they actually published a validation study on 2 helps to be. So again, this was validated on an entirely different population. In this case, this was 2,000 patients at 3 different hospitals. And then once again, you can see that the risk predictions hold up. So one of the things that they did as part of the study was that they used 2 helps to be to allocate CEG monitors at their own ICUs. So if you had a high score, you were kept on for a standard 3 days. If you had a low score, you were only kept on for CEG for an hour. And then using this rule, they were able to allocate CEG monitors on the basis of stroke risk. And then in this way, they were able to monitor more patients, but reduce the overall amount of CEG monitoring. And then, this led to about $6.1 million in savings at the ICUs at Massachusetts General Hospital and the University of Wisconsin. So that's an estimate in fiscal year 2018 using the Medicare billing rate of $1,000 per CEG per day. Okay. So let me just wrap things up with a summary. So in this case, I spoke about a project that focused on disuse. And the big picture strategy behind it was to build to develop a new method to build models that were already being adopted. So the method that we designed fit models by solving a hard optimization problem, and it produced models that performed better, that could easily be customized, and that produced useful guarantees for model development. And then in this case, all this really depended on our ability to solve this optimization problem. So here, the existing algorithms we could use weren't reliable, so we developed a new one. And then, we use our algorithm to fit risk scores, but it could work for any empirical risk minimization problem with a convex loss and discrete constraints. But, big picture, I think ultimately the benefit of all this was that we were able to use our method to build models that were adopted and that led to benefits. Right? So the ADHD model that I showed you is being deployed at primary healthcare clinics in the United States, and it screens way more effectively than the previous screener. And then the seizure model that I showed you is, leading to large savings in the setting where, it's really difficult to adopt any new technology. Okay. So that's all I wanted to say about this project on disuse. And what I want to do now is shift gears and start discussing a project about misuse. Okay. So the starting point for this next project are consumer-facing applications of machine learning. And so by consumer-facing applications, I mean, applications where machine learning is used for things like credit scoring for hiring, for determining who's eligible for healthcare services like Medicare or Medicaid, right? So these are all, potentially powerful use cases of machine learning, and they're use cases that we keep on hearing about. But I guess, what's scary is that we keep hearing about these systems and we keep finding out that they result in harm. And when they do, there's really no appeals process. So over the last couple of years, we've been hearing more and more about regulation as a middle ground in this setting. For example, here's the Algorithmic Accountability Act of 2019. This is a bill that says that consumer-facing models should be fair and transparent. And this is a good step in the right direction. But the issue with this bill is that it doesn't come with a technical specification. All this bill is saying is that we should audit the models, but it isn't really clear what types of tests we should run. So in this case, there's actually a lot that we can learn from credit scoring. And the reason why is because, well, credit scores have been regulated since the Equal Credit Opportunity Act was introduced in the 1970s. So one of the key regulations that came with this act was the right to an adverse action notice. And what this says basically is that, in the US, when you are denied credit, you are entitled to a list of principal reasons for this denial. So this is a regulation that was designed at a time where credit decisions were being made using models. And it's effectively the longest standing right to an explanation from a predictive model. And as a regulation over the last 60 or so years, this has been rather ineffective. And the main reason why is because, well, models don't provide principal reasons for their predictions, right? So here's a simple model that's used for lending. Here it is denying credit to an old lady who has no income, no savings, no credit history. And in this case, it's clear that the old lady is being denied credit, but it isn't so clear what the principal reason is for the denial, right? Is it the variable that's the most important? Is it the variable that has the most points? And this lack of technical specification in the regulation is a real problem, right? So credit scoring companies in the United States basically don't know how to comply with this law. So everyone has come up with a heuristic solution. And the solution they've come up with is mainly designed to get regulators off their back, not necessarily to help consumers. But from a consumer point of view, this isn't even the most useful question to be asking, right? Like what we should really be asking for the consumer is, what can this person change in order to be approved for the loan in the future? For that question, that specific question that has an answer, we could tell this person basically that they could change their income or their savings, and that could help them in the future. Now, turns out that this is a much more interesting question to ask. And the reason why is because, well, sometimes models might not provide any actionable changes. Okay? So here's a model denying another loan. This time it's to a 22-year-old UW student who just graduated with a well-paying job, income, savings. Okay? And in this case, there's no change that this person can make that would allow them to be approved for the loan, right? This person can't get older, and they can't build credit history if they keep getting denied for the loans in the first place. Okay? And now this is something that might be wrong, right? And the reason why is because, well, here you've denied this person credit, but you've also denied them the ability to qualify for credit for at least 10 years. Okay? And then without taking a hard stance on whether this is right or wrong, what I want to point out here is that by asking this question, we were able to produce a concrete piece of information that would be of interest to a regulator and the consumer. So in this project, we really wanted to study this type of behavior because it was related to a type of harm that could be verified. And we did it by introducing a new concept that was called recourse. So formally, recourse in machine learning is your ability to obtain a desired prediction from a fixed model by changing actionable input variables. Right? So these are variables that a person can actually change, like their income and their savings. And recourse is not explainability, but it's still something that's important, right? And the reason why is because, well, say in the previous example that you were denied a loan. Well, there should be something that you can do to change that decision. If you can't, that means that your decision will be fixed, and more importantly, that the model will have stripped away your ability to control your own creditworthiness. So recourse really relates to your autonomy in the model's decision-making process. And that type of autonomy is really important when a machine learning model is used in applications with equal opportunity regulations. So things like credit scoring, health insurance, the allocation of public services. So, from the intro, you know that models might not provide recourse because they contain immutable variables. What I want to point out here is that this can happen in many different forms, right? You might have models that take a long time to change. You could have variables that can only be changed for some values, not others. You could have variables that you don't know you have to change or that you shouldn't have to change, like your marital status. And in practice, you could govern recourse by drafting regulations that talk about what types of variables a model could use. But it turns out that this isn't really a practical approach, right? And a good reason why is because, well, a model could use completely kosher variables and then still deny recourse by requiring drastic changes, right? So a model could say something like, for instance, you can qualify for a loan if and only if you increase your income by $10 million. And then something like that could change based off of the model's deployment population. So in practice, if you really want to protect recourse, then you need to check the feasibility of recourse and check the difficulty of recourse. and then do this on your model's deployment population. So the main technical contribution of our project were tools to do exactly this without interfering in model development. So the tools that we developed let you answer questions like, what is the feasibility and difficulty of recourse of this model over a population of interest? And what can a person change to obtain a desired prediction from a given model? So both our tools worked using a simple integer programming routine. So what this thing does is that it takes in the model, it takes the data for a person who is denied a favorable outcome, and it takes a set of valid actions for that person. And then it solves an integer programming problem. And the output of the procedure is either an action that will flip this person's prediction, or definitive proof that this person doesn't have recourse. So integer programming is really critical in this setting for two reasons. Right? So the first is just modeling exact actions. Right? So if model, for example, has binary variables, ordinal variables, categorical variables, then actions are discrete. And integer programming will allow you to model that discreteness and to find actions that are feasible with respect to those variables. But the other reason why integer programming is really critical here is to prove that a person doesn't have recourse. Right? So in some sense, what's really hard here isn't finding a feasible action, but it's proving that someone doesn't have recourse. And that's because when actions are discrete, to prove that someone doesn't have recourse, you've basically got to search over all possible actions and make sure that none of them will flip the prediction. So what do you need to know? Well, we've designed this routine to work with all possible linear classifiers that include certain types of rule-based models. Our routine supports specialized cost functions that might be nonlinear or non-convex. And the last thing you need to know is that the routine is fast. So we've implemented this using an open source solver as well as a commercial solver. And in all cases, it usually takes way less than a second to run once. Okay, so how do we use this thing? So the first way that we use it is to do what's called a recourse audit. So here, I'm just showing you standard performance plots for a set of credit scoring models that are built using the UCI credit dataset. And here I'm showing you 10 logistic regression models that were trained with different L1 penalties. And you can see that as you increase the L1 penalty, the accuracy of the model changes slightly, and there are fewer variables. So in a setting like this, a practitioner who's developing these models could run an audit for each one of them using either training data or data from the model's deployment population. And so what that would involve is, for each of these models, you would call our routine for everyone who's denied credit, and then you'd count the number of people who have recourse, and then you'd measure the magnitude of changes that they have to perform through a cost function. Okay? So that would produce plots like this. Here on the left, I'm showing you the feasibility of recourse for each model. And on the right, I'm showing you the distribution of the cost of recourse for all those folks who have recourse. Okay? So here, the cost function that we're using is based off of percentile changes. And specifically, it's the minimum percentile change in any input variable that's required to flip the prediction. Okay? So, a cost of 0.4 means that any action must change at least one variable by a 40 percentile shift. Okay? So a 39 percentile shift in one or more variables would not flip the prediction. And now that isn't the end-all be-all metric of difficulty, but it's something that's standardized, that's communicable, and that accounts for the distribution of the variable in the target population. Okay. So the next way that we use this is to build what's called a flip set. So here, to motivate this, say that we deploy one of the models, then we're given a person who is denied a loan. So we have to comply with this adverse action regulation and produce an adverse action notice. So in this case, we would call our routine to enumerate different actions that would flip this person's prediction. So we'd call it once, get an action, then we'd remove that action from the feasible region using discrete constraint, and we'd call the routine again to get a second action, and then again, and again. So here, this flip set has 4 items. Each item shows a specific set of changes that a person could use to flip the model's prediction and qualify for the loan the next time they apply. So here, the person could have increased their latest payment from $0 to $790. They could have paid off their balance in full, or some combination of two. Okay. And in this case, the cost function that we're using is also based off percentile changes, but it's localized. And then what it says is basically, changing your income from the 50th to the 55th percentile is easier than changing it from the 90th to 95th percentile. So together, both these tools let us protect consumers in different ways, right? So something like an audit could be used in model development, in model procurement, in an algorithmic impact assessment. Something like FlipSet could be used to inform consumers via regulations like the adverse action regulation. But it could also be used to check recourse and deployment, right? So even if you didn't want to show this list to a consumer, the act of producing it in deployment would let you check that recourse isn't violated by your model. Because basically, if this table is empty, then that means that this person doesn't have recourse, and that way that's a red flag for you to go and check your model, make sure that it provides recourse to a consumer. Then stepping back, I think the broader message here is that it's much easier to protect consumers from harm in these types of applications if we focus on concepts that come or that allow for a technical specification. Right? So in this case, we focus on this concept of recourse, and that's important because it relates to individual autonomy. But it's also helpful because it's something that can be verified and for which we can produce a rich family of tools to check for recourse. So we're building on this work by adapting our tools to check recourse for other types of model classes. And another project that we're pursuing is on how to create flip sets that have causal actions using a predictive model and observational data. But what's been really exciting, right, is that over the last year or so, people have really taken this concept and developed it in completely original ways that we've never thought of. So now there's, for instance, work on the philosophical basis for recourse. There's work on how to build flip sets for black box models and causal models. And then there's also work, for instance, on recourse and recommender systems, right? So in a recommender system, recourse relates to your ability to obtain a specific recommendation from a recommender system. So if you don't have recourse, that really means that you're pigeonholed into a certain recommendation profile. Okay. So I presented projects to deal with each type of last mile problem. And then in both of these projects, these methods that I spoke about involved solving hard optimization problems. But I think that what was really important here was formulating the right problems to begin with. And in some sense, I was really lucky in working on these projects just because they were areas where there was a rich history of these models being put into practice, right? So scoring systems have been known for about like hundreds of years. Something like the adverse action requirement has been known for about 60 or so years. So in both cases, I think, there was this rich history that let me figure out what user needs were and design effective methods. But going forward, I think that a lot of the most interesting applications of machine learning are going to be in these areas where there is no history. And in that sense, I am really excited to work with folks in areas like human-computer interaction to figure out what user needs are and to design appropriate methods for these cases. So going forward, I think another thing that I'd like to do is just use applications to drive method design. So in these last few minutes, I just want to quickly outline a few directions for future works. And in all these cases, I'm going to be focusing on healthcare applications. So this first direction I want to just quickly mention, we'll start off with a seizure application. So this is another model that we developed while working on 2LCB. And this was designed to use fewer CEG patterns. And the reason for this was that instead of having doctors check for CEG patterns, we're actually training neural nets to detect these patterns. So this is going to produce a fully automated system for seizure prediction. And what's going to be special here is that the system is going to be fully human verifiable. So here, a doctor can check how the front end of the system works. This is just a simple linear model. But a doctor can also check that the backend models are working correctly, right? So for example, if one of these pattern detectors detects a certain CEG pattern, well, doctor can always go back to the raw CEG screen, make sure that pattern is already there. And in that sense, a doctor is more likely to trust the system because they can check that each of these components is working correctly. So what's cool with this type of setup is that we can really customize the front end. Say, for example, a doctor knows that when all these patterns are detected, well, we're going to get a seizure. Well, that's something that we can bake into the front end as a prediction constraint. Or say, for example, the doctor thinks that one of these pattern detectors is less reliable than the others. Well, we can train the front end as a decision list and then force that item to be the last item in the list. And in that way, we would have minimized reliance on that certain pattern detector. So I think that systems like this are going to play an important role in healthcare, and that's because I've seen several of them, right? So here's another system that we built from MGH. This one is used to predict readmissions risk. Here, the data are unstructured clinical notes. The backend is composed of NLP pattern detectors for different tags, like whether a patient has chronic illness or mobility problems. And the front end is a simple scoring system that predicts the risk of readmission for that patient. So what I'd like to do going forward is really work on formalizing this approach. And I believe that it involves a huge set of technical problems that relate to areas like active learning, like data collection, and also just trust and user studies. And I'm just excited to do this by collaborations with doctors, as well as folks in computer science and in the Department for Human-Centered Design and Engineering. So another direction that I'm really excited about is fair machine learning for healthcare. Okay. So, there's been a lot of work in fair machine learning over the last couple of years. Fairness in healthcare is a relatively new topic, and it requires a different approach. And the reason why is because, in healthcare, a lot of data sets already contain protector attributes like age and sex. And it's okay to use these attributes for prediction, but only if you can do it in a way that doesn't harm the groups that are related. So what I'm interested in here is, how to build models that perform well on different subgroups without making assumptions on how those groups are different. And another topic that I'm really interested in here is, how to repair kind of models that exhibit performance disparities in deployment, right? So say, for example, you've trained a model to predict lung cancer from an X-ray, and it exhibits a performance disparity on a very specific demographic. Well, is there a way that I can, repair that model by devising a patch without necessarily having to train an entirely new model? So we have work in both of these directions that we presented at ICML last year, but I think there's a lot of work that's still left to be done. And again, I'm excited to pursue it in collaboration with doctors and folks in technical areas. Okay, and then this last research direction that I'm really excited about is data-driven discovery. So here, to start, the applications I have in mind are in areas like bioinformatics. And specifically, I'm really interested in these simpler tasks where we're working with classification and regression models. Right? So in this type of setting, a lot of models are built to recommend experiments, and they're typically fit using convex optimization techniques. And at a high level, I think that there's a lot to gain by using discrete optimization in this setting. So here, directions that I'm interested in pursuing are how to train, customized models that incorporate domain knowledge. And I think that, those types of models would lead to experiments that are more readily performed by lab managers. And then another direction that I'm interested in pursuing is, how to produce a large set of competing models. So in a lot of these applications, by producing a set of competing models, we're producing a competing set of recommendations for experiments. And, in that case, we should basically prioritize experiments that are recommended by the set of all competing models. And, if there's an experiment that's only recommended by a single model, maybe we should put that lower down on the list. So on that note, I'd like to end by thanking a number of my collaborators. And then we can stop there with some time for questions. Thank you.
Great. Thank you very much. And apologies for the strange silence post-talk. Okay, so I'm going to behave as moderator for questions for Burke, and I know a couple people are probably going to have to run, but anyone who has a question, if you could please use the raise hand feature in the Zoom button. Thanks. I can start us off while some people try to find that button.
Sure.
At least for me, I always have to look for it again. Okay, so my primary question relates to the emphasis on linear models. So in general, when you're using linear models, they have a lot of the nice properties you're talking about. They're easy to interpret. They're easy to, do computations as a function of counterfactuals, all of these sorts of things. But on the other hand, they fundamentally cannot describe direct interactions between combinations of variables, right, of features. And I'm curious, in the domains you were talking about, sort of how much accuracy you left on the table by only considering linear models or like decision trees over very small numbers of linear models, things like this, because I feel like I didn't get a sense of that at all.
Yeah, no, so this is a great question. So let me just, yeah, so in a lot of domains where, so not with the project that I presented today, which is on risk scoring, but with its predecessor, where we were creating models that output yes/no decisions. We did a lot of these types of comparisons between, for instance, linear models and other families of models. And what we found is that basically on, basically tabular data sets, there isn't a large loss in accuracy that's left on the table by using linear models, or by using our specific linear models. Now, there are a couple things that are going on here. One is that, with a lot of the variables, we're including binary thresholds, so we might be able to capture nonlinear effects in a single variable. Another thing that's happening is that, when we're fitting the models, we're optimizing kind of discrete objectives, whereas like the competitors are optimizing convex surrogates because they're optimizing over a more complex model class. And then the last thing is that, this observation was really limited to, like simple tabular data sets where it's possible to actually apply our technique. So in each, so I mean, I can refer to a couple of papers and other things where we've done these types of comparisons. And, the methods that end up doing better are things like stochastic gradient boosting and like SVM with an RBF kernel. But the increase in accuracy is generally like to the order of like 1 or 2 percentage points. Yeah.
Yeah, that's helpful. Great. Alex.
Yeah, hi, thank you for the talk. I kind of wanted to piggyback on that question and hear your thoughts about where it's good to stay with, especially with the doctors like this, score-based decision-making, and where is it good to go with what the doctors are comfortable with and know and will use versus trying to bring them more into the machine learning aspect and try to, I guess, bridge the gap between machine learning and what doctors generally use.
Yeah. So I guess the question is, yeah, like when you have these problems that involve like a user in the system, is it better to change the system or the users? I mean, I think honestly, let me think a little bit about this. Is this a good question? I mean, to be honest with you, I'm open to both aspects. Like philosophically, if both approaches end up resulting in better outcomes, that's great. I find that in a lot of settings, like the models that I'm showing, I mean, it's not just that, like in a lot of settings, the models that I'm showing, it's not just because like doctors can understand it, but it's also partially because you can kind of customize them to obey different types of operational constraints. And those are things that might be important for the model when it's actually deployed. So some of these models that I showed today have like prediction constraints, or they're fit to like, optimize accuracy at a very specific operating point. And those are also important considerations that might be harder to deal with when you're, working with kind of generic models that might be less understandable to doctors. Beyond that, I think, I mean, generally speaking, I think that for the applications that I worked with, doctors I think are generally willing to adopt technology so long as they can like verify that it's correct. So, you know, I mean, when you're doing that, I think having like prototypical examples, having explanations are all useful things that could work. But I don't know. I mean, I think, you know, if you're able to do both, do both. But I don't have a general like, you know, rule of thumb being like, oh, use this approach here, use that approach there.
Great. Should we ask Sue-Anh for one last question? I know we're running a bit over time.
I know, yeah. I have many questions, but given that we will have one-on-one tomorrow, I'm going to ask just one of them. So it's related to Jamie's question. Not only you lose expressive power if you use linear model versus complex model, you can also lose an ability to have, you know, represent the feature interaction terms, which can be really important, and it can help you understand the model better. It helps interpretation. And then medical data especially, you know, a lot of things can interact with age, for instance, and or sex. And then, you know, what is your take on that? I mean, do you have a way to address that by, you know, staying in this like linear model you are using, or I don't know, yeah.
Yeah, no, yeah. So I think there are several approaches depending on what the application is like. I think that, you know, on a first order basis, like in practice, when I'm fitting these types of models in applications, I will always compare to a baseline that includes these nonlinear effects, and then and I look if there's a big gap in accuracy. Say for example that there is. In that case, I would probably use an explainability technique to try to figure out exactly where those interactions are taking place, and then we can do things like use constraints to include certain interactions if they improve accuracy. So we could say something like, oh, like include this interaction between age and sex if it like improves accuracy by a certain amount. So there are ways to be able to deal with it, but it doesn't automatically select it and it doesn't automatically show it. So you have to use external methods to be able to see that. But at the end of the day, the benefit is just that, like, you know, you still get this ability to customize it and deal with other types of constraints that might be important that you wouldn't get in these other settings. I think beyond that, another kind of important way to deal with things like age and sex, just because is like if age and sex really describe different demographic groups, then I think it's important to check whether or not it's better to build like a single model using all of the data or different models for different groups. So when you deal with the different models for different groups, I think that you know, that can deal with a setting where the heterogeneity between the groups can't be represented through interactions, or might not be well represented through the interaction form that you've specified. So we found a little bit of that happening, and I think that it's relevant in healthcare just because, you know, in healthcare it might be okay to train separate models for separate groups, and that, you know, it might be reasonable to expect that there might be heterogeneity between groups. But yeah, I mean, we can discuss a little bit more about it later tomorrow as well.
Okay, thank you.
Great. I think because we're running out of time and it's relatively late for Brooke today, let's give him a thank you again. And thank you very much. Enjoy the rest of your day, and I'll see you tomorrow.
Great. Thank you. Thank you everyone for being here.